Very good morning to everyone. This is PRIYANKA, Assistant Professor, EC Department, TKRE. Today in our lecture, we are going to study about digital modulation techniques. Before going to study digital modulation technique, let us know some of the basic terminologies in communication system. What is modulation? We have to know this. The modulation is the process of superimposing high frequency carrier signals with low frequency message signals, resulting in a modulated wave. So that means high frequency carrier signals are superimposed so that we get a resultant modulated wave. In this modulation, one of the three parameters of the carrier is changed. That is either amplitude, frequency or phase according to the amplitude of the message signal. So modulation can be defined as a change in amplitude, frequency or phase of the carrier in response to the message. It is also important to increase the range of communication or to increase the signal to noise ratio and decrease the size of antenna. So modulation is helpful in increasing the range of communication, in increasing the signal to noise ratio and decrease the size of antenna. Let us have a look about types of modulation techniques. So there are basically two types, analog modulation and digital modulation. Analog modulation. In analog modulation, both carrier and message signals are of analog waveforms. Whereas in digital, only carrier is analog, whereas message is in digitalized form. Okay. Then what is our topic? That is digital modulation technique. Now we will have a look about our topic. There are mainly three types of digital modulation technique. So if you look back, digital modulation technique is nothing but in digital modulation, only carrier is analog, whereas message is in digitalized form. So now the basic types of digital modulation techniques are amplitude shift keying, frequency shift keying, phase shift keying. The term shift keying means that amplitude, frequency or phase of the carrier wave is shifted between two or more discrete values rather than varying continuously like analog modulation. That means it is shifting in between zeros and ones. So we got the name shift keying. Let us observe the first technique, that is amplitude shift key. The amplitude of the resultant output depends upon the input data, whether it should be a zero value or a variation of positive and negative, depending on the carrier. That means the carrier is varying in accordance to the message input signal, that is either 1 or 0. So output signal, if you observe this picture clearly, in ASK modulated output, whenever the signal message signal is 1, we can observe the signal. Whenever the message signal is 0, there is absence of the signal. The same thing is diagrammatically shown here. You can have a glance about it. Next, we will see how this ASK is defined in terms of expression. And let us also have a look about demodulation, advantages, disadvantages and applications of ASK. Let us have a look about ASK. The strength of the signal is varied to represent binary 1 or 0. Both frequency and phase remains constant while amplitude changes. Commonly, one of the amplitude is 0 As we discussed previously, whenever there is a binary 0, we can't observe any signal in the modulated waveform. But if there is a binary 1, we can observe the carrier signal. Now, coming to the demodulation, the presence or absence of sinusoid in the given time interval need to be determined. Okay. Coming to the advantage, it is simple to implement. Disadvantage, it has very noise interference. It is susceptible to noise interference. So noise usually affects the amplitude. Therefore, ASK modulation technique mostly affected by noise. So as it is simple, coming to the advantage, but disadvantage is noise interference is much when compared to the other two FSK and PSK shift keys. Coming to the application, it is used to transmit digital data over optical fiber. This is all about ASK basic definition. Let me again recollect the thing. First of all, we'll study about ASK waveform. So input is message signal and output, the carrier signal varies in accordance to the message signal. If input is 1, you can observe the signal. If input is 0, there is an absence of the signal. And for the same thing, if you write the expression, S of t can be written as A cos 2 pi fct for binary 0 and binary 1, A1 cos 2 pi fct. And whenever binary 0, the A0 cos 2 pi fct is completely represented as 0. Coming to the advantages, it is simple. Disadvantages already we have discussed. Noise interferences. Right. Now let us see what is FSK technique. The FSK of the output signal will be either high or low depending upon the input data applied. That means whenever the input data is high, you can observe there is a high frequency in the modulated waveform. If the input message signal is 0, you can observe a low frequency in the modulated signal. So the first waveform is describing the message signal, second waveform is the carrier, and third is the modulated signal, where whenever 1 is there, you can observe the high frequency. Whenever 0 is represented, you can observe the low frequency. Coming to the modulated signal representation, S of t is equal to A cos 2 pi f1 of t. That means binary 0. Whenever binary 0, I am taking a representation as A cos 2 pi f1 t. Whenever binary 1, I am representing as A cos 2 pi f2 t. In some cases, you can also represent as 2 pi flt for binary 0, 2 pi fht. In some textbooks, you can find as fl and fh. You can also represent as f1 and f2. The same thing what we have discussed here always. See here f1, that is representing the binary 0. Its frequency is always lesser than the higher frequency which is representing the binary 1. Coming to the demodulation, the demodulator must be able to determine which of the two possible frequencies is present at a given time. Advantage, FSK is less susceptible to errors than ASK receiver for specific frequency changes over a number of intervals. So, noise spikes can be ignored. Coming to the disadvantages, FSK spectrum is very much greater than ASK. That means bandwidth increases. Coming to the application, over voice lines and in high frequency radio transmissions, we can go for FSK. Right. So the main drawback is the bandwidth is high when compared to ASK. Advantages is it is very much less susceptible to the errors compared to the ASK. Next modern digital modulation technique is phase shift keying. The phase shift keying can be also classified into two types. One is BPSK, the other is QPSK. BPSK is nothing but binary phase shift keying, whereas QPSK is nothing but quadrature phase shift keying. And there is also one of the DPSK is one of the special case of PSK, okay, which can change the phase according to the previous one. So totally we can study under PSK, we will study BPSK, QPSK and DPSK. Okay. So if you observe the waveforms of PSK, the first one is explaining about the message signal. The first waveform is message signal. Second one is carrier. And the third one, whenever the symbol 1 to 0 is shifted, whenever message signal is traveling from 1 to 0, you can observe a shift of 180 degrees. And from 0 to 1 also you can observe a shift of 0 degrees. So that means from 1 to 0 you can observe 180 degrees, 0 to 1 you can observe a phase difference of 180 degrees. This is about your binary phase shift keying. So in binary phase shift keying, you can take two symbols 1 and 0 combinations, where you can observe only two phase shifts when the bit is variable from 0 to 1 or 1 to 0, you can observe a shift of 180 degrees. Coming to the representation of modulated signal of PSK, A cos S of t can be written as A cos 2 pi FCT when binary 1, and when binary 0 is transmitted, we can represent the modulated BPSK as A cos 2 pi FCT plus pi. So further plus pi is nothing but we can also write it as minus A cos 2 pi FCT as shown above. So example binary 1, 0 phase shift, binary 0, 180 degrees phase shift. Right. Now coming to the demodulator, must determine the PSK phase of the received sinusoidal with respect to some references phase. Advantages: PSK is less susceptible for errors than ASK, while it occupies the same bandwidth as if like ASK. More efficient use of bandwidth. That means the bandwidth of PSK is lesser than FSK, and it is almost equal to ASK. Coming to the disadvantage, more complexity in detection or recovering process than ASK and FSK. Now, once again, let us have a clear study about BPSK. So, as we studied previously, BPSK consists of two phase reversals. One is 0 and the other is 180 degrees. So, when the message signal is shifting from 1 to 0, you can observe a 180 degrees phase shift, and similarly from 0 to 1 also you can observe a phase shift of 180 degrees. So it will be always in between 0 to 180 degrees. So this is 0 at 1 And at 0, you can observe the 180 degrees of phase shift. The figure is very clear. Whenever there is a signal, message signal is 1, you can clearly observe the sign is starting from 0.0 degrees. And whenever the message signal has been shifted from 1 to 0, you can observe the 180 degrees of phase shift. Coming to the QPSK, the other type of PSK, here we can observe 4 phase reversals. In previous case, BPSK, you have only 2 phase reversals, that is 0 degrees and 180 degrees, whereas here you can observe 0 degrees, 90 degrees, 180 and 270. 4 phase reversals you can observe. And as it is having 4 phase reversal, we can also observe that the input binary is taken a combination of 0, 0, 1, 0, 0, 1, 1, 1 bits. It is a 2-bit combination. So when the input is 2-bit combination and the phase reversals are in between 0, 90 degrees, 180 and 270, then we call it as QPSK. The waveforms of QPSK are clearly observed here. You can observe the waveform. Whenever there is a 0, 0 combination, the waveform is started as 0. When it is 1, 0 combination, you can observe a 180 degrees of phase shift. When it is a 0, 1 combination, it is a 90 degrees phase shift. And when it is a bit 1, 1 combination, you can observe a 270 phase shift. Right. Now let us see the third type of PSK, which is a special case of PSK. We can also tell differential phase shift key. In this differential phase shift key, the modulated signal is shifted relative to the previous signal element. There is no reference signal considered here. The signal phase focuses the high or low state of the previous element and it starts with phase reverse. If you observe a combination 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0 combination, as I have taken an example. Here you can observe when both the bits are 0, 0, there is no phase shift. And whenever you are observing a message signal which has been shifted from 0 to 1, there is a phase reversal. And again, you have a combination of 1, again one more phase. And from 1 to 0, there is no phase reversal. From again 0 to 1, you can observe a phase. That means DPSK is purely depending on the previous bit. If it is active high, then it starts phase reversal, or else it will stay in the same previous phase. Now let us see amplitude shift keying modulator. The ASK generation method or modulator is shown as in figure. At first, we are taking a switch type of structure. For that, one of the input is given as a sinusoidal carrier and the other input is given as a our message signal, which is a unipolar binary signal. And whenever the input binary is 0 is transmitted, the switch will be open, and binary 1 is transmitted, the switch will be closed and the carrier is followed or transmitted to the other end. When the switch is open, there is no transmission of signal. The same thing you can observe with the help of this block diagram. And further, for shaping of the signal, we are using a band limited signal. After applying a band limited signal, we are getting a ASK output, which is a modulated output. So you have to concentrate on the points like binary sequence when the message signal makes unipolar input to be either high or low. Whenever there is high, carrier is allowed, or else there is no signal as it is switch is open. So no signal is allowed for. Coming to the ASK demodulator. Demodulator or detection process can be done with the help of two methods. One is asynchronous. We can also call it as non-coherent method. The other is synchronous method, which is also called as coherent method. So what is the difference between synchronous and asynchronous? The clock frequency at the transmitter when matches with the clock frequency at the receiver is known as synchronous method, or we can also call it as coherent method. Otherwise, that means if the clock frequency of the transmitter and receiver are not in synchronous, then we call it as asynchronous or non-detection, non-coherent detection. Now let us see synchronous ASK demodulator. So in synchronous ASK detector, we can observe the block diagram where my input is ASK modulated signal input, and I'm giving that input to a square law detector so that my amplitude gets squared, and then I'm applying that amplitude to the low pass filter so that all the high frequencies are eliminated. And then the signal is given to a comparator so as to compare whether the input signal is above threshold or below threshold. And finally, we are going to get a data signal output which is either 0 or 1. The same thing you can also have a look about this. Synchronous ASK detector consists of a square law detector, low pass filter, a comparator, and a voltage limiter. The ASK modulated input signal is given to a square law detector. So always square law detector will have a square of amplitude modulated input voltage, and low pass filter will minimizes the higher frequencies as we have discussed, and the comparator and voltage limiter will help a clean digital output based on the conditions like threshold value. Coming to the FSK modulator, this is what you can observe. The FSK modulator consists of input binary data, then an on-off level encoder, then finally we have a product multiplier with carrier 1 and carrier 2. And before coming to the product modulator at carrier 2, we need to apply an inverter so that M of t is applied to the carrier 1, the upper part of the modulator, and inverter, that is M naught of t bar, is supplied to transmitted to your lower part of the modulator. And when the outputs of these two modulator are summed up, then we are going to get a binary FSK signal. So FSK modulator or generator is shown as in the figure. Coming to the FSK demodulator, here also we can observe two methods, asynchronous and synchronous. Synchronous detector is also called as coherent. Asynchronous is also called as non-coherent detection. Here let us have a glance about asynchronous FSK detector. If you observe in the figure, the input is my FSK, and then I am giving for a pulse shaping, and that output of that pulse shape signal is given for envelope detector, and finally we are giving for a decision circuit for output. Right. So the block diagram is as such. The FSK signal is passed through a two band pass filters, and the output of these two band pass filter look like ASK, which is given to envelope detector. The signal in envelope detector is modulated asynchronous. The decision circuit choose which output is more likely to the selected one, and according to that it will generate a rectangular form based on zeros and ones. Coming to BPSK modulator, you can observe the block diagram. BPSK modulator, the balanced modulator is given with one input as carrier wave generator, the other input is a binary sequence data, and output is our PSK wave. Right. Following, in this we can observe the BPSK demodulated block diagram. We can observe a BPSK signal coming from a channel that is applied to a square law device, and further it is band pass applied to a band pass filter, and then a frequency divider for the synchronous demodulator or multiplier, and then an integrated circuit you can observe. So what is happening here? So S of t can be calculated as or expressed as B of t under root 2p cos 2 pi f naught t. That means amplitude A can be further written as under root 2p. So when that is my S of t is given to a square law detector, it simply squares the value, and further if you send to a band pass filter, only particular band is passed. That means only higher frequencies are allowed. And when we give for the same thing for a frequency divided by 2, the 2 which we are observing here is cancelled, and finally cos 2 pi f naught t plus theta is sent to a synchronous detector, and one of the input for this synchronous detector is the other form V of t under root 2p cos 2 pi f naught t plus theta, which is a phase shift value of the first input. So when we combine both the values, then we got, when we multiply both the values, it is B of t under root 2p cos square 2 pi f t fct plus theta. And if this particular value is given for an integrator, then it will be directly proportional to S of KTB is directly proportional to B of NTS. So B of NTB means we are going to get a binary data. The same thing with the help of block diagram, whatever I have explained is also shown with respect to expressions. Here the first expression is S of t is equal to a cos 2 pi f naught t is our first and foremost expression. Further I am representing amplitude with respect to under root 2p. That means power is equal to amplitude, that is RMS value by square root 2 whole square. If you take, it is a square by 2. So a is equal to further root 2 p, and that under root 2 p is given for a square law detector. You can observe the same thing here. So what is happening in the square law detector? It squares the cos terms. So cos square theta can be written as 1 plus cos 2 theta by 2. We already know that expressions. So finally, you are left over with a DC value of 1 by 2 plus the other one is cos term. So when you give that particular signal to a band pass filter, the DC term is neglected and you are having only a cos term. And further, this cos term is sent to a frequency divider so that the factor 2 gets cancelled. And finally, this output is given to synchronous detector, and further that multiplication value can be represented as B of t under root 2 t by 2 1 plus 2 2 pi f naught t plus theta. So this is how the binary sequence and BPSK is modulated and deep. Coming to the QPSK modulator. So the QPSK modulator uses a bit splitter to multiply us with local oscillators, a 2-bit serial to parallel converters, and a summer circuit. And the form block diagram is as follows. So here in QPSK, we are going to separate odd bit terms and even bit terms, and they are separately applied to a product modulators. And to that product modulators, one of the input is even or odd bits, and the other input is taken from the local oscillator, and the local oscillator signal is phase shifted and given to the as an other input to a lower part of the block diagram, which is also called as quadrature. And in phase PSK is the upper part, we call it as in phase, and quadrature lower. When you sum both the signals, you are going to get this QPSK output wave. So the QPSK for 2 bits input is as shown. So when 0 0 combination, we are taking a 0 degrees of phase shift. 1 0, it is 180 degree shift. Coming to 0 1, it is 90 degrees phase shift, and 1 1, it is 270 phase shift. And this is what the block diagram of QPSK demodulator. The QPSK demodulator uses two product demodulator circuits with the local oscillators as shown again, two band pass filters, two integrated circuits, and two parallel to serial converters. So here again we are giving my input as QPSK input, that is given to a product modulator as one input. The other input is taken from the local oscillator, and further it is given for a band pass filter so that pulse is shaped. And if that particular signal is given to an integrator, then you are going to get the even bits and odd bits in parallel. Again, we need to convert that parallel to serial data. This is what DPSK modulator. The DPSK is a technique or of BPSK in which there is no reference phase signal. So as already we have discussed, DPSK purely depends on the previous input, not any reference signal. And the following block diagrams explain the DPSK modulator, where a serial data input is given as one of the input for the XNOR gate, and the other input is taken as a delay from the output. And when such combination is given to a balanced modulator as an one input and the carrier as other input. So from this feedback circuit, you can say that it is present purely depending on the previous value, but not any reference signal. So therefore, DPSK is defined as is not depending on any reference signal. And even DPSK encodes in two distinct signals, that is 180 degrees phase shift each. Coming to the DPSK demodulator, the figure is as shown in that the phase of the reversed bit is compared with the phase of the previous bit. And that is given for a balanced modulator. And further, low pass filter is applied so that all the high frequencies gets cancelled. And we are giving for a shaper. And we recover the original binary data as an output, as shown in the figure. Coming to the special technique, which we call in digital modulation technique is QAM, that is quadrature amplitude modulation. Quadrature amplitude modulation, QAM. So basically QAM uses two-dimensional signaling. Originally information stream is split into two sequences, that is odd and even, as shown here. So AK sequence is in phase component is modulated by cos 2 pi fct, whereas quadrature phase components are modulated with sine 2 pi fct. So here you can say it as two-dimensional signaling. So QAM uses two-dimensional signal. So combination of two-dimensional signaling is AK cos 2 pi fct plus BK sin 2 pi fct is sent to you through the channel. So if you observe the modulated output, AK is a sequence which is in phase component is product multiplied with cos terms, whereas BK are multiplied with sine term. And further you will get a combination of AK cos 2 pi fct, BK sin 2 pi fct. Further they are given for a summing. So you will get your output modulated QAM as AK cos 2 pi fct plus BK sin 2 pi fct as a transmitted signal. An example of QAM you can observe here. So 00100111, a 2-bit combination I have taken. I have separated all the odd bits and even bits. So first bit combination 0101 and the other bit combination 00 and 11. Odd bits and even bits are separated. And for odd bits I am giving a sine waveform. For even bits I am giving a cos waveform. And therefore when you give for a product multiplier, two product modulators we are using for sine and cos. So you can observe a 90 degrees phase shift that indicates one is sine, the other is cos. So phase difference between sine and cos is 90 degrees as we know. So output of these two signals is given for a summation to get a QAM modulated signal. Coming to the demodulation of QAM. Here our original modulated signal, which is AK cos 2 pi fct plus BK sin 2 pi fct, is further multiplied with 2 cos 2 pi fct and 2 sin 2 pi fct. And then it is given for a low pass filter for smoothening. And then you get your bits AK and BK separate. So AK are odd terms or BK are even terms or in phase terms, quadrature phase terms. So all the required calculations can be done with the help of the basic mathematical expressions. They are cos square A can be written as 1 plus cos 2 theta by 2 or 2a by 2. Sin square theta is equal to, we know that 1 minus cos 2 theta by 2. So using this basic mathematical functions, you can calculate the values as such. So let us have the overall glance again about digital modulation techniques. In this lecture, we have completed all the digital modulation techniques, basic techniques. So what are the basic techniques of digital modulation? ASK, FSK and PSK. Further, PSK is classified into BSK, QPSK, BPSK, QPSK and a special case of DPSK. And we have, other than these three techniques, further we have a QAM modulation technique, which is a combination of PSK and ASK. Is QAM technique. So totally we have learned three basic things: phase amplitude shift keying, frequency shift keying, phase shift keying. Three basic techniques plus QPSK, DPSK, QAM. So totally 6 modulation techniques. In that, the main three types are ASK, FSK, PSK. So shift keying is nothing but the amplitude or frequency or phase of the carrier is shift between two distinct values, that is either 0 or 1. So these are the figures we have studied under ASK. So when message signal is 1, 0, then the binary output is observed. Whenever binary 1 is there, you can observe a signal. Whenever binary 0, there is no signal. So ASK, as we represented. Coming to the FSK, whenever binary 1 is there, the frequency of the signal is high. Whenever binary is 0, the frequency of the signal is low. That is, whenever binary 1, it is FH, or binary 0, it is FL representation, lower frequency. Coming to the PSK waveforms, whenever 1, we observe the signal starting from 0. Whenever 0, the signal starting from 180 degrees of phase shift you can observe in between 1 and 0. And let us also observe the waveforms related to QPSK. So in QPSK, the signal is, the phase of the carrier is shifted in between 4 different degrees, that is 0, 90, 180 and 270 as shown in the figure. And BPSK signal, whenever active 1 is there, then you can observe a shift in the value. It is completely depending on the previous value, but not on the reference value. So this is what ASK modulator or generator. So where ASK mode generation method is done with the help of a switch. When is binary value 1, you observe a signal. Where binary is 0, there is no signal. And this is what ASK demodulator. In demodulator, we have two techniques, synchronous and asynchronous. Let us have a glance on synchronous ASK demodulator once again. So block diagrams are very important in ADC. So have a glance. So ASK demodulation consists of square law detector, low pass filter, comparator, and voltage. Coming to FSK modulator. So whenever frequency high, we are giving a carrier frequency F1 is given to binary. Whenever binary input is high, F1 frequency is transmitted. Whenever binary 0 is transmitted, low frequencies are transmitted as modulated signal. Coming to demodulation methods, also we have asynchronous and synchronous. So we have a look on asynchronous FSK detector. So it consists of bandpass filters, envelope detector, and decision circuit. BPSK modulator, a balanced modulator is given with inputs carrier and message signal, and output you are going to get a PSK waveform. This is what the BPSK demodulator. If you compare all the three methods, ASK, FSK, PSK, the performance of PSK is more when compared to that of FSK and ASK. And bandwidth is higher in FSK when compared to PSK and ASK. And noise interference is high in ASK when compared to that of PSK and FSK. So these are the points you need to remember. I just want to have a glance on the block diagram so that QPSK modulator, odd bits and even bits are separated and they are given separately to a product modulators, and finally we are giving for a summation. This is what QPSK demodulator, where you can observe QPSK input is given for product modulators with an local oscillator, and further they are given for an integrated to get a DC values, digital bits, zeros and ones. And then we are giving for parallel to serial converter. This is what DPSK modulator. So where you can observe serial input data is given for an X node, and further one of the input of the X node is taken from the previous value, and that is given for a balanced modulator. Then we get DPSK signal. And this is what the demodulation process. Again, we are giving a delay bit to the balanced modulator, then low pass filter and shaper to recover the binary data. This is what the special digital modulation technique, that is QAM. So it uses two-dimensional signaling. And here the QAM modulated process is observed here. So we are using two product modulators and a summation again. Coming to the QAM demodulator technique, we are using a balanced modulator or product modulator, and then that particular output is given for a low pass filter to get in phase and out phase, quadrature phase binary sequence. Thank you for watching this video. I hope you have I hope it is very clear about all the digital modulation techniques. Thank you.